Okay, this is just a quick video about writing repeating decimals as fractions. So we can do things quickly, and then if you like, well, I won't know, but I'll explain how. So first, the quick rule is if you have a simple repeating decimal, and simple repeating decimal means something like a third, right? Or something like, I don't know, any of these, where everything behind the decimal gets repeated. The rule for these is pretty simple. You take that same number, write it over 9. Or if there are 2 digits, you take those numbers and you write them over 2 9s. Or if there are 3, you take those 3 and you write them over 3 9s. So for simple repeating decimals, that rule is pretty quick and easy. If you have something that doesn't, I'm going to call them mixed. If you have something that doesn't entirely repeat behind the decimal, something like 0.75 repeating, and only the 5 repeats. So that's 0.75555. So this bit all repeats, but that one doesn't. Then you take that number and you write it over 9 0. There are 2 digits. One of them repeats, one of them doesn't. One of them gets a 9, one of them gets a 0. Then, we're not done yet, sorry. You take that number on top and you subtract the 1 that doesn't repeat. So this 7 didn't repeat, so I'm subtracting it. So 75 minus 7 should be 68 over 90. And of course, with all fractions, at the end you'd want to reduce. So you'd write 34 over 45 or whatever. Like up here, you'd write 1/3, and you can reduce, it looks like, at least this one too. I'll do one more example of a mixed one. I don't know why I wrote mixed again, but okay. Let's take something like 0.3395, and the 95 is repeating. So that's 0.3395959595 forever. So we would do the same deal. We would take our 3395. We would write it over 2 9s for 2 repeating digits, and 2 0s for 2 that don't. These 2 that don't get the 0s, and these 2 that do get the 9s. And we just have to subtract the digits that don't repeat. So in this case, 33. So we would take 3395, subtract 33, I get 3362, I guess. These numbers are not important, I just grabbed some random ones, over 9900. And then of course, just like any other fraction, if you can reduce, you should. Right. I'm going to pause for a second here. Okay, so we've had the short version of how to convert a repeating decimal into a fraction. And the explanation I'm going to give you is also a shortish explanation, but we'll see how you like it. So say we have some number that we don't know what the decimal form is. That number might be something like 0.555 repeating. So we could write that as 0.5 with a bar over top, that ligature to say it's repeating. If we want to convert this into a fraction, we could say, well, I'm going to use some algebra. We'll call that number x. This 0.5 repeating, we already know what the value is, but we're going to call it x because we're going to do a little trick to it. So if we have this value, x of 0.5 repeating, we could also do stuff like multiply stuff by x, right? 10 times x is the same as 10 times 0.5 repeating, which is 5.5 repeating. Now, if we take 10x and x, And we have our 10x, which is 5.5, repeating, and our x, which is 0.5, repeating. If we were to subtract these two, we would notice we may notice something interesting, which is that the 0.55555 over here and the 0.5555 over here will always cancel out. This 5 and this 5 will make 0, this 5 and this 5 will make 0. However many there are, we'll get 0. The only thing that doesn't cancel out is this digit over here. So that's 5.0. So if we do this, 10x minus x, 10 minus 1 is 9. That's 9x. And 5.5 repeating minus 0.5 repeating is 5. Now we have an expression here. 9x is equal to 5. If we solve for x, we're looking to divide this side and this side by that factor of x. So x times 9, we can divide by 9 so that we can cancel out to just get x. And we're allowed to do that as long as we do the same thing on the other side. So we can say x is equal to 5 over 9. In that way, we can see why we get the 5 over 9. I'm going to do one more example. This example is going to be a little bit longer. It's going to be with a mixed repeating decimal. So where we have a few digits that don't repeat yet. This is going to be kind of a big jump in the explanation. So if you're happy with your understanding here, that's okay for Math 10. I'm gonna keep talking though for a couple minutes. So let's pick another example of a number. Let's pick let's make it actually repeat. So this 5, 4, 5, 4, 5, 4, 5, 4, this is going to be 5.6345 repeating. The 4, 5 just keeps going over and over and over. So if we look here, these digits repeat and these digits don't. So now we can't just do the same trick as before with the x and the 10x, because we have to play with the decimal that's a little bit further over to the side. If we want to move this decimal over to where the repetition starts, that's 2 places. 2 places to the right is the same as multiplying it by 100. So 100x, if I want to move that decimal over the right, 563.45 repeating. Now if we take, for example, a chunk of that number that has some of the repeating decimal, the first 2 instances, that's going to be 1, 2, 3, 4. So we have 1, 2, 3, 4 places to move it over. And why I'm doing this, I think, will become obvious, or it may become more obvious in a moment. That would move this over the decimal 5, 6, 3, 4, 5, and then we get our repeating decimals over here. So in this case, I've got more zeros in there than I did in the previous example, but that's just because the repetition happens further to the right, further on down the line. If I do the same kind of trick where I take 10,000x and I subtract the 100x, I'm going to get 10,000 minus 100, which is 9,900 x's. And on this side, if I take my 10,000x, which is 56345.45 repeating, and my 100x, which is 563.45 repeating, the same thing happens over here. Past the decimal, everything cancels out. There is no decimal. And if we do 56345 minus 563, we get 2. We've got to carry a little bit, borrow some zeros, etc. We should get an 8. Eventually we'll get a 7, a 5, and that 5 stays alone. if this part here, you're saying, how did you get 55782? You can practice carrying with the borrowing ones, etc. That should be something you've got well under control by now, though. So now we have 9,900x equals 55,782. We want to solve for x, which means we divide by everything that's not the x over here, so we can cancel. And we're allowed to do that as long as we do the same on the other side. So we get x is equal to 55,000, this is an ugly example here, 782 over 9,900. And you can check that out on your calculator to say, is this actually the same? And it should be. This trick where we're taking multiple versions of the x, multiplying by 10 or 100 or 1,000 or whatever, to shift the decimal over to the side, setting two equations next to each other, subtracting them, finding the value, getting an expression like this expression right here, and solving for x, is what we're really doing when we are doing the short version, which we said up here, which is where we take our repeating decimal and throwing it over 9, or if we have a mixed one, throwing it over 9 with however many zeros behind it. This is what's going on behind the scenes to get that 0. And that's what's going on behind the scenes to get these number of 9s as well. But the short version is, if just everything behind the decimal is repeating, you can count that number of digits, throw them over that many 9s. Reduce if you got it. If there's only a few digits that repeat, we end up taking that whole thing that's behind the decimal, all the digits behind the decimal, subtracting just the one digit that doesn't repeat, and throwing it over as many 9s as there are repeating decimals, and as many zeros behind that as there are non-repeating. And the reason for that is because we're doing something like this step here. We're taking two versions of the same equation, shifting the decimal over so that we can tidy it up so we only get repeating decimals, and then just solving for x. That may or may not have helped, but there you go.